What is organic chemistry? We kind of briefly talked about this already. We're looking at the study of carbon compounds. We've got our nucleus holding our protons and neutrons, and then our electrons on the outside. Talked about what things those defined as, and everybody seemed to be happy and okay with all that information, at least so far. Where did our electrons exist? All right. When we look at, I'll grab you. When we look at the nucleus, we could put all our protons into one nice tiny little package. And the reason we could do that was because of the neutrons that helped minimize that charge repulsion. But what happens when we've got our electrons? Can we condense all of our electrons into one tiny little position? No. Okay. One of our reasons, we have charge-charge repulsion, so that negative-negative repels them away. And then we don't have another subatomic particle to help glue them together. So we end up putting in our electrons around our nucleus in such a way that we kind of minimize that charge repulsion. Okay, so we'll put them in closest to the nucleus first. Why would we go closest to the nucleus? Minimizes the charge. Okay, we're getting it as close to that positive. So this is one of the big lessons that you'll see happen again and again through organic chemistry. What we're concerned about, I think you just came in, right? Is minimizing charge. Oh, and you, sorry. Minimizing charge and going to the lowest energy. So we always want to put a positive near a negative. Okay, we never want to put positives next to each other. And if we have a molecule that has a positive charge, we can start to predict what it's going to do. Okay, if I put that positive charge into a new environment, what is it going to search for? Something negative to cancel out that positive charge. So when we're looking at our nucleus with all that positive charge, we want to minimize that positive charge as best we can. We'll start to bring our electrons in closest to it, because the closer they are, the more we can cancel that charge, both on the nucleus and on the electrons. We can't put all of our electrons in the exact same space for the same reason. Not the same reason, but we could get away with doing that with the protons because we had the neutrons to minimize that charge repulsion. We don't have that particle. So we have to start layering our electrons further and further away from the nucleus. Okay? If we looked at our energy levels, so that's what the colored diagram is supposed to be showing on the left. Is that the left? That is the left. Okay? You'll notice that the gap between those energy levels gets smaller and smaller and smaller. Why would it get smaller? Okay, why don't we get even divisions all the way up?
The further the electron is away from the nucleus, the more it wants to push back towards it.
Cool, a reasonable idea. The further it goes away, the less it's being held by that positive charge, so it can actually start to get further away. But then why don't we just see this infinitely go on where it gets higher and higher in energy all the way out? We'll see some overlapping too. What happens if I put an electron, let's say these are all my energy levels. I get it right? 1, 2, 3, 4, 5. Let's say, I think that's actually all of them. What happens if I get an electron up here? Where is that electron?
Valence shell.
It's outside of the valence shell. What do we mean by what's outside of the valence shell? It's not attached to the atom. Okay? So what we're looking at is the extreme energy that we can get for any electron is the vacuum, where it is no longer associated with any atom. So when we're looking at putting our atoms together, we're concerned about putting our electrons into these systems where they belong with an atom. Would we expect to see an electron free floating on its own? Okay. We don't see them free floating on their own. Why not? They're negatively charged. That charge is inherently bad. We've put a lot of charge now in something infinitely small. Remember, if we look at the mass of an electron compared to a proton, it's 1 over 1835, the amount of the mass. Okay, so it's really, really tiny. Well, somebody will say, well, what about electricity coming out of the wall? Okay, well, where are the electrons coming out of the wall? Is that just a free flow of electrons? They are transferring through a sea of electrons of atoms, of metal atoms, and the electrons are passing through the electron shells of those metal atoms. They are still associated with those individual atoms, okay, those metal atoms. Okay? And if we want to still push this kind of analogy with the outlet further along the lines of, is this charge an inherently unstable thing? Okay? And I always make this statement, and then somebody goes out and does it. Don't do this. How are we taught as kids with forks and electrical outlets? Don't do it. Okay? We don't stick them in there. Why not? The electric charge comes out and hits you. Charge is inherently a high energy state. It's very bad. The electrons in that electrical outlet are trying to find a lower energy state. And if you stick the fork in there, it's going to find that lower energy state through you, which is not a particularly nice thing to do. Okay? So whenever we're trying to put things together or do these individual reactions, what we're ultimately trying to do is shift those electrons to a lower energy state. Okay? Yes, we could potentially go through and quantify this. And this is typically where you get people not liking organic chemistry. So give me a number to associate it with. Okay? Unfortunately, at least the way we're going to teach it, because you don't want to see the other version, we see very little numbers. We do not quantify those energy states. Okay? We tend to go through and say the electron is better here than it is here. And we have some superficial ways of approximating that, and those approximations work phenomenally well. But you have to kind of realize we can't associate a number with it all that easily. Okay? So we could start to put our electrons in that lowest energy. Well, I guess questions about any of that. Okay? As we slide our electrons now in, if I only have 8 energy levels, how many electrons could I potentially put into this? Okay, we got a couple ways we could process this. Electrons repel each other, right? So if I got 8 energy levels, I want to put those electrons as far away from each other as possible. I only get 8 electrons. What element does that get me to? Not very far along the periodic table. So there's got to be something else going on. Okay? What's one thing for something else going on? There's actually 2. Okay, we could look at shells. Each of these energy levels has a redundancy where some of them will split into multiple different energy levels, if you will. Okay? And we get our different orbital types. Okay? What orbital types do we have? S, P, D, F. I think technically you can go all the way out to G, although we haven't gotten anything out there. Okay? In theory, it could go on forever. Okay? Why does it not go on forever? It's unstable. The nucleus would fall apart with too many protons in it. Think about where our electrons go. Eventually, we start putting our electrons so high in energy that to get to the vacuum, they just kind of have to fall over. Say, okay, well, I'm going to be in the vacuum then. Okay, you're putting me at too high of an energy state. So we could go through and separate these out into different shells. You'll notice that our shells first show up with that blue level, which is our second energy level. Okay, why do they not show up for the first one? It's a harder question than I meant to ask. Anybody have a good answer? You can put 2 electrons on each of our energies. So we could drop 2 electrons here, 2 here, whoops, 2 here. So I'm not sure I follow your statement. Huh?
It's smaller.
Not sure I follow that one either. I would argue that actually it's going to come back to quantum physics. You're looking at wave functions and how electrons move, and we really don't want to do that.
That's what I was about to say.
Yeah. Okay. So what we're doing is looking at how those energy levels can split. The higher up in energy we get, they can start to split into different orbital levels. Okay. We can get those different orbital types. Okay. And we can end up putting 2 electrons in each. As we move up in energy, we can add an extra orbital type to each of these. Sorry, I thought I got to this part. Okay. If we went through and then classified this, even with adding those extra shells, you'll notice that we still probably won't cover all the elements on our periodic table. Okay, what else happens? if you had to give a name to this orbital, could you name that one for me? Our lowest energy level. So it's S, 1s, okay, because it's that first energy level. What happens when we move up to the next one? 2s and 2p. And we moved even further up. Where's my green? 3s, 3p, 3d. There's something else going on? Particularly at the 2p. What happens to the 2p? The 2p orbital has 3 subsets. So what we end up doing is branching each of these continuously outwards. I guess that should be in blue. We're going to color code this. And we could now put 2 electrons. So you would miss that if you were at lecture. You didn't see me do that. In each of those. Okay? So we can now start to see how we could propagate this all the way out. Okay? This is one of the reasons why inorganic chemistry is interesting, because inorganic chemistry, and I don't mean general chemistry, everybody thinks that. There's something else called inorganic chemistry. Starts to look up at that 3D energy level. No, that green doesn't show up. And we get 5 of those shells. Okay? Well, if we're looking at organic chemistry, we're concerned about how carbon interacts with other molecules or other atoms. Okay? Well, there's a lot of other atoms on this periodic table, and a lot of them have 3D orbitals or 3D electrons. If we're going to be concerned about how carbon interacts with another molecule, I need to know where all of those electrons are and how they interact with each other. Okay? That's a pretty tall order. Okay? Thankfully, organic chemists said that's way too difficult. And we went through and simplified to a certain extent. Instead of looking at all of the electrons within an individual atom, what do we end up looking at? The outer shell. Why do we care about the outer shell? Those are highest energy electrons. Okay? Still goes back to that stability argument. We want to make those high energy electrons as stable as possible. Our 1s electrons are already really low in energy. Why mess with them? They're already happy. Okay? So what we're constantly trying to do is look for that highest energy and say, hey, how can I tweak that? Is it possible for me to tweak it and put it in some other place that makes it happier? Okay? That was odd. Why did it do that? Oh, that's why it did that. So we could go through and look at the images. I'll pretend that you didn't see that. What were our shapes? Okay, so for our s orbital, how many times is that split out? None. Good answer. Okay, what is the shape of an s orbital?
Sphere.
It's a sphere. Why does it not split out into multiple orbitals? Take a sphere, rotate it. What does it look like?
Sphere.
Sphere. Rotate it again. What does it look like? Can you tell that it was rotated? No. When we're looking at our orbital levels and the splitting options, it's an orientation of those orbitals. If we take an s orbital and I change the orientation, I cannot tell a difference. I can't tell that the orientation was changed. Hence, we end up with only one possible orientation. What happens when we move up in energy? Okay, we'll still get these spheres building on top of each other. So we could look at the 1s, the 2s, the 3s, okay, so on and so forth. What happens if we jump up one more level? Okay, we look here. Well, I'll call it red because the red shows up a little bit better. What was our next? P. What happens with our p orbital? What does a p orbital look like? Dumbbell. What happens when you rotate or change the orientation of the dumbbell? Can you tell that the orientation changed?
Yes.
Yeah. What ends up happening? We classify 3 possible orientations. Okay? And we get those different possibilities. We get an x, and a y, and a z axis. Okay? What happens if we move up one more energy level? We get the D. What does the D look like? Cloverleaf is the standard explanation for it. Splits out into 5 energy levels. You'll notice that it doesn't work out perfectly. the fifth energy or the fifth orientation is not a clover leaf. Okay? Where did all these shapes come from?
Electrons spend most of their time in probabilities.
It's probabilities, it's how an electron moves, which goes back to a wave function, hardcore quantum mechanics and calculus, all sorts of other junk that I was horrible at. Okay? But they do a really good job of explaining this. The overall shapes that we get are ultimately our interpretation of the mathematical plot of this. So you'll typically see drawings we see for the S here, okay, and you see for the P up here. Okay. Those drawings represent the mathematical plotting of all of the possible places that our electron could potentially exist. So it's ultimately a probability. We look at those shapes and say, well, that looks like a sphere, so I'm going to draw it as a sphere. For the p orbitals, that looks like a dumbbell, so I'm going to draw it as a dumbbell. Okay? The drawings that we use are the 95% probability. It might even be lower than that. It might even be the 90% probability. Okay? And we don't care about the rest of it because most of the time we aren't going to see our electrons out there. We aren't going to see electrons of that energy floating around. Okay? So it doesn't make sense to look at our structures in that fashion. Okay? Particularly when we jump down into the D. Okay? I can understand a sphere. That looks pretty reasonable to me. I can understand a dumbbell. I've been to the gym a couple times. I've seen those. Cloverleaf? Okay? Particularly changing the orientation of a cloverleaf. Because it's not just here's an X, a Y, and a Z axis. I'm looking at all these weird freaking orientations. It's not particularly easy to deal with. Okay? This is why organic chemists are cool. What did we say? You're right, that is way too difficult to look at. So you know what? I'm not. Okay? Carbon. Where's the energy level for carbon? It's our second energy level. We only have the s and p orbitals to worry about. We do not have to worry about the d orbitals. Those d orbitals only show up in that third energy level. Yes, they can play a role, and we'll have to evaluate them a little bit, but for the most part, we can ignore the d orbitals altogether. Okay, so that's a nice little step up that I think organic chemistry has over general chemistry or even inorganic. Okay, you also lose a lot of the cool complexity, but hey. Okay? So when we look at the periodic table, okay, an organic chemist tends to get really blurry about everything outside of what's shown up here. Okay? So if you ask me about anything to find even iron potentially, okay, the only reason I can find iron now is I taught 130 last semester, so I had to refer to iron fairly frequently. Okay? Before that, I had no clue where it was. Tungsten, one reason why I know tungsten, it's just a weird symbol. Everybody seems to forget what tungsten looks like, so I had to ask that question. Okay? We ignore that section of the periodic table, the D's and the F's. Okay? You'll notice even further that there's large sections of this. This is still, to me, I think, awfully difficult. Okay? There's still, I can't count fast enough. What do we got? 20, 30 elements in there? Whew. I don't have enough fingers, okay, or toes. So an organic chemist looks at this again and says, you know what? That's still too difficult. Okay? And we condense down, okay, and my little drawing missed one. We condense our periodic table down to what looks like we're pretty close to now 10 elements. Okay? We will see other ones pop up every so often. Sulfur shows up. Okay? But for the most part, all of our understanding for organic chemistry, at least at this level, is centered on those elements and how they interact with each other. Okay? Are there some important patterns that you might remember from general chemistry? Okay? It's, again, another section of the textbook that is almost always glossed over in 151. What are some periodic trends? Electronegativity, going to be the absolute most huge, important trend that you will need to have stuck in your brain. And we'll look at some simplifications of it. But in general, what's the most electronegative? Fluorine is our most electronegative and our least. I mean, it's a little bit weird here. I blacked it out. The opposite corner, okay, is our least electronegative. Okay? So we want to have that general pattern memorized, because that's going to help us interpret a lot of how we do bonding and other things like that. Okay, so electronegativity is a big trend to watch for. What else? Atomic radius. Are you cheating? You're kind of cheating. You're looking at the slides. Okay. We can look at radius. Okay. How does our atom size change? Okay. What are the trends with atom size? Okay, there's an angle on it, so there's typically two things you have to remember for atom size. We go left to right, what happens to our size? Okay. And it depends what you're looking at, ionic versus atomic. Okay. But in general, our atomic size gets a little bit, I don't know why I'm writing size. We usually get a little bit smaller. What happens as we go down? Bigger. Again, an organic chemist looks at this, oh, that's 3 different things I have to memorize. So what do? Within a row, they're roughly the same. Within a column, we see a substantial change in the size. Why is the size change so much more dramatically down a column? You're putting, and it's not even that you're having so many more electrons. If you go boron to carbon, you're adding electrons. If we go boron to fluorine, you're adding a lot of electrons. What's the difference about where you're adding the electrons when you go down a column? The next energy level. Okay? That's a substantial difference. Okay? So remember that when we think about size, when we're looking for trends. Within a row, same. Down a column, it gets bigger. Okay? Because you're putting those electrons further away. Okay. Last trend that'll kind of come important when we're talking about the first chapter and then usually kind of disappears. Stop talking about it. Since you got it pulled up, what was the last one?
Orbitals.
Orbitals. Okay. We had those S, P's, and D orbitals. Okay. Those are going to be important when we're determining our valence shells and trying to figure that out. Where are our S orbitals? We take a look at our periodic table. To the left. Those first 2 columns are typically referred to as the S block. The section from boron to officially our noble gases, the P block. All right. That gives us some information about where our electrons are and what electrons we need to be counting. All right. If I want to figure out the valence electrons for carbon, what do I have to do? Yeah, everybody does that. I hate that. I never memorized that. That's why I hate it. So what I do, since you guys all have a better method, is you can count out the rows. Okay? And remember that this D section, remember as an organic chemist, I can't see that. I get confused by it. So I go 1, 2, 3, 4. 4th row, 4 valence electrons. Column, thank you. 4th column, 4 valence electrons. If I want to get up to our halogens, 4, 5, 6, 7. Okay? So I can just count the number of columns. Okay? Extra little reference on this. Since we're really only dealing with the first element in those columns, we typically don't have the big fancy names for them. The alkali metals, the alkaline earth. If anybody made you memorize that, I'm sorry, I'm not going to memorize that because I don't know the difference between them. Okay. There's also the other ones. You may have heard of chalcogens, pnictogens. You guys like those ones?
Never heard of them.
Never heard of them. The only reason I like them is they sound cool. It's fun to say chalcogen, fun to say pnictogens. Really the only name that you're going to be responsible for, because I'll say it a lot, is that column with our fluorine and chlorine and bromine and iodine, our halogens. Okay, that's going to be our primary one. We'll group the halogens all together because chemistry is all about the same. Okay? There is some variation, which we'll see later in this semester. Okay? So we've simplified our periodic table. We got a rough idea on our general trends with this. Okay, so now how do we push this to compounds? Well, if we take 2 atoms and we bring them near each other, okay, eventually they're going to interact with each other. Okay? What's going to be the result of our interaction is one thing to consider. The other thing is going to be what factors are going to control that interaction. Okay, so the first thought process that I would think about here is, what's the first thing that's going to interact between these 2 atoms?
Electrons and the protons.
It's the electrons. Okay. Hugely important for organic chemistry. The first thing that interacts when we're looking at how anything's come together are the electrons. So if I'm going to look at an organic chemistry class, what's the thing that I'm going to want to move around the most? Electrons. So we will use something known as curved arrows to show how the flow of electrons move. Hence, if you remember that, I'm not sure if I referenced it, pushing electrons in the recommended, it says required, but the recommended things on the syllabus, okay, that helps you understand how to move electrons. Why? Because that's the first thing that interacts. Okay? So we're looking at how those electrons change their general locations with respect to their atoms. Okay? What other factors could control that interaction?
What types of atoms they are?
Okay? We could look at the types of atoms. What about the types of atoms? I think I heard it. What did you say? Someone say? Metal or nonmetal? What's different when we're looking at our metals and nonmetals? Electronegativity. Think back to our primary trends that we just discussed. Electronegativity, size, and what orbitals are going to be involved. Okay? Those are going to be our primary concerns, at least in organic chemistry, on how those things contribute. Okay? What are the possible interactions? Some people started listing them out already. We get a bond. Okay? Are all bonds created the same? No. So we could get varying bonds. How do we determine what bond was present? Well, that depends on the conditions of our interaction. What things are controlling it? Our electronegativities. Okay? That kind of deal. Okay? So our electrons, we're going to move up from just defining the charge on our atom to really determining if our reaction can occur. How do those electrons shift around? That's going to determine our system. Okay? So we add some possible options out of here. We already discussed this. Option A, we get a strong attraction between those electrons, okay, or between our atoms, and we end up forming a bond. Or what happens? They could potentially repel away from each other. We don't get a bond. And we said that there are possible variations of bonds. Do you think there's possible variations of not bonds? Yeah, why not? Turns out there are. I would actually take it a step further, and not bonds typically carries a different name. Are intermolecular forces. Okay? So really what we're going to divide organic chemistry into is looking at making bonds and looking at these forces and seeing how the interplay between those gets us from one place to another. Okay? So what are our types of bonds? Okay, that was a bad question. Let's try that again. Which is your favorite bond? Hydrogen bond. Interesting call. What's the issue with hydrogen bonds? Why is that not up here?
It's kind of a covalent bond.
It is not a bond.
Oh.
It's a force. It's a horrible name. Okay, but it is not a bond. It is a force. We will talk about those eventually, but I don't think we were going to reach them in Chapter 1. James Bond was an interesting reference, particularly from the previous slide, right? Yeah. I thought it was classy. Okay. We've got these three possible bonds. Okay, so let's pick one. Let's pick ionic. How do you know you have an ionic bond? Okay, very left and very right. What's our big difference between very left and very right? You're right. Okay. Metal, am I writing the right spot? Yeah. Metal and a nonmetal. Okay. Nice, easy way to represent it. Is that our strict definition? No. There's a more accurate definition. Okay. What we're looking at in the variation between these, ionic all the way down to covalent, is how well the electrons are shared. Well, ultimately, what controls how well the electrons are shared? Electronegativity. What's our definition of electronegativity? The ability of an atom to attract not electrons, technically.
Protons?
Bonding electrons. Okay. It's a very subtle difference in the definition. Okay, but we're looking at bonding electrons. Okay. If we look at just electrons, what word applies to that definition? That one's a stretch. Again, only because I had to teach it recently do I remember it. Electron affinity. Okay? That's attraction of any electron. Okay, so we can look at metal and nonmetal as a nice definition, or we could go back to a difference in electronegativity, difference being our delta symbol for electronegativity. Good, no one's going to challenge me. I think it's chi. I think that's chi. Chi, chi, whatever. Our difference in electronegativity being greater than 1.7. Okay? That number changes depending on the textbook, so we got to be very careful with that number. Why is that strict definition pretty useless?
Figure it out every time.
I would argue it's not a pain to figure it out. We could look up the electronegativity of carbon and electronegativity of hydrogen and see that difference and calculate it. It's pretty easy.
Thought we were lazy though.
Yeah.
What's going on here?
Okay, you've been listening to my lectures? Organic chemists are inherently lazy. The whole process of having to open up a book to figure out some numbers to then punch into a calculator, because we can't do simple math, okay? Way too difficult. So what we want is some approximative definition. The approximated definition, metal and a nonmetal. Very simple, very easy, okay? And when we're looking at that, we would tend to classify that what's happening with those electrons. Are they being shared?
No.
Typically say not sharing of electrons. So let's push the extreme of that. What's the complete opposite? Or I could throw in a little trick phrase. What's the complete polar opposite? It's covalent, not polar covalent. It's the trick phrase. Okay? We're looking at non-polar covalent. The complete opposite is that we have a difference in electronegativity that is now technically less than 0.5. Okay? Or we could look at the complete opposite. The difference in electronegativity is 0. When's the only time we get a difference of electronegativity being 0? Same atom to the same atom.
Or
Turns out,
if it's in the same row.
not the same
That's
row.
the same size. There
Yeah,
we
it's
go.
size. We could go through and try and use that difference in electronegativity each and every time. It's going to get a bit tedious. Okay? And we could always just say it's always the same atom with the same atom. But then that's such a narrow, restrictive definition that we can't really apply our observations of the real world back to it. Okay? So that's why we get this 0.5. So how can we real quickly look at a molecule with the individual atoms and say, that's a nonpolar covalent bond, or that's an ionic bond? So we came up with one. So nonmetal and nonmetal, tricky. That is technically true, but it's not always going to give us an electronegativity that small. Okay? So I would make the argument that that definition isn't going to work very well for us. So I can go ahead and cross some of these definitions out. They're true, they suck. Okay, we can't look at metal and metal. That's going to be metallic, and that's a whole other can of worms I don't want to deal with. I could draw a Lewis structure for sodium chloride that's going to look the exact same as methane, carbon, and hydrogen.
Formal charge.
We could try and do something with formal charge, but again, depending on how you draw the Lewis structure, you may not see that formal charge. You guys already came up with one of the definitions. Anything bound to itself is technically a bad way to phrase that, but that's how I would phrase it too. So we had a carbon bound to a carbon, bromine to bromine. Fluorine said was the most electronegative. So we would typically expect anything with fluorine in it is going to be an ionic bond. But if I bound fluorine to fluorine, difference in electronegativity is 0. That's a nonpolar covalent bond. We've got a big issue with these two different definitions, though. Or, sorry, we didn't finish our nonpolar covalent. That definition we said is so restrictive it's not going to help us out. We need to add one extra little statement to that. And I know we asked it in 130, because I asked it. And I'm pretty sure I saw it on 151 exams as well. There's an extra definition that we typically classify as nonpolar covalent. It becomes really relevant for organic chemistry. That refers to the polarity of the molecule. We're talking about a bond. Two different atoms, we don't have a symmetry issue. Carbon to hydrogen. Oh, that's a good thing that showed up on the slides. Okay. Carbon to hydrogen is typically classified as a covalent bond. Okay? So if you look at an individual structure and you see anything bound to itself, nonpolar covalent. If you see carbon bound to hydrogen, nonpolar covalent. For the rest of this class, you will always hear me refer to this category, in this case our purple definition, as covalent. Okay? Remember that lazy statement? Nonpolar covalent is too much effort. Okay? So we're looking at these as covalent. We now have this big gray area in between. Okay? We got this polar covalent section. Okay? So we could go based off of both the ionic and our polar covalent and say, or sorry, our covalent bonds, and say anything that's left is going to be our polar covalent. Okay? That could work pretty well. Anything else? Polar covalent. Okay? Officially, it's going to make up the difference in electronegativity, that gap in between. Okay? Because we've simplified our periodic table down, I would actually change this a little bit further and say we're looking at anything bound to oxygen, nitrogen, or a halogen. Why would I pick those three? And technically halogens are four, but what's the electronegativity of our first halogen, say fluorine? It's the highest. What's our next highest electronegativity? Oxygen. I think it goes oxygen, nitrogen, chlorine are tied. Okay. What we've just selected are the most electronegative non-metal atoms out there. So if we put anything next to them, we're now generating a polar covalent bond because they are naturally going to draw that electron density away because they are the most electronegative. Okay? This can now help us apply things because we can now look at a structure and very quickly say ionic bond, covalent bond, polar covalent bond. Why is that important? Of these, which ones do you think are going to react the most?
Ionic,
Why ionic?
because they dissociate into ions.
Dissociate into ions. What's special about ions? They are charged. Charged is where all of our reactions occur. Okay? To get an ionic bond, we need a metal and a nonmetal. This is organic chemistry, so typically we don't see metals show up, at least in first semester. They do show up every so often in second semester. And what would we predict of those compounds? They are stupidly reactive. Okay? And this semester, we're not going to quite get as far as those super reactive species, so we'll stick into our polar covalent and our technically non-polar covalent bonds. Of those two, which ones do you think are going to react the most? Polar covalent, because that difference in electronegativity starts to generate partial charges. Those partial charges are then what will react later on. Okay? So if we had to take a prediction between methane and, say, water, which one would we say is more reactive? Anybody know the structure for methane? CH4. And water, H2O. The one that's more reactive would be water because of that polar bond.
Hydrogen.
Okay? Well, don't get into hydrogen bonding yet. We'll open that can of worms later. Okay? So now what I kind of want to go through is looking at Lewis structures. I've summarized all of the rules. These come from, I think, when I first taught 151, and have since kind of modified them and changed them around a little bit. Based on textbooks that I've seen, my version is different than most versions. Okay? And one very subtle, slight change. Ultimately, it makes no difference whatsoever when coming to a correct Lewis structure. Where it makes a huge impact is one of the most important topics for organic chemistry when trying to find resonance. You talk to most general chemistry instructors, what do they think about resonance? Oh, don't worry about it. You won't need to do that until you get to organic chemistry. Thanks, guys. Appreciate that. So the big subtle difference, okay, is going to come in rule number 3. Okay? We want to add electrons in pairs to the most electronegative atom first. Most people start putting the electrons in pairs around the central atom. Oh, because the central atom needs bonds. True. Okay? But if we're in a situation where resonance is going to come into play, putting them around the central atom, 9 times out of 10, prevents you from seeing the resonance. Okay? And we will look at an example here in just a little bit. Okay? If we put the electrons first around the most electronegative, we can find that resonance structure much quicker. Okay? Why does it make sense, for that matter, beyond just this resonance argument that I seem to be, inventing? Okay? Why does it make the most sense to put the electrons there first anyway?
That's where they're going to go.
It's the most electronegative element. By definition, it is attracting all bonding electrons towards it until it can't attract anymore. It makes the most sense to put them there first because they already want the electrons. Okay? The rest of these, particularly if you remember 151, will end up simplifying greatly, and you'll end up probably never thinking about this again. Chapter 1 has a lot of Lewis structure type drawings because ultimately what we want you to do is practice it enough that you ingrain this kind of process into your brain, and that when we think back to that simplified periodic table, we can look at a structure and say, yes, that's a valid Lewis structure because I know all the possible ways that carbon can bond. I know all the possible ways nitrogen can bond. So we can put those together very quickly after we've done enough practice to memorize it. Okay? So this is where the quiz is going to come up. And we will do a couple examples here, but I'll give you 2 minutes. I did mean to put the what that name question back on here, but I forgot to. So, and I'm serious about 2 minutes, and I might keep talking. So, 2 minutes, provide the following. Structure for CH4. I want the total valence electrons that go into the Lewis structure. I want the Lewis structure. Give me the electron geometry, the molecular geometry, and the hybridization of the carbon. Yes, we will be talking about each of these this semester, so if you don't remember, it's okay. I'm just trying to get a feel for what you remember from potentially 2 years ago. Just CH4. Just CH4. The examples section I should have timed out, but I didn't. Examples for drawing out our Lewis structures. Let's do CO2. Where do we start? Valence electrons. This is where the math gets pretty hardcore as far as organic chemists go. I know some other organic chemists will go into more, but I'm really bad with numbers. Okay? So we'll count up our valence electrons. How many valence electrons does carbon bring in? 4. How many valence electrons does oxygen bring in? 6. How many oxygens are there? 2. So we can multiply that by 2. Get our total. What's our total? I'm going to trust you. That was bad at math. Give me a break. Okay? Central atom. Typically our central atom is the least electronegative. There are some exceptions to that. Look back to the previous slide. So our least electronegative in this case is carbon. We can then scatter our other atoms around it. Up to you how you want to scatter them around it. This is one of the downfalls of Lewis structures that we'll talk about. Lewis structure has no concept of necessarily where those atoms are in a three-dimensional space. Lewis ultimately, when he built his theory, built atoms as cubes. Okay, that he simplified down into squares. How many sides are there on a square? 4. Okay? And he said 2 electrons could fit on each side, which meant 8 electrons. There's our octet rule. Okay? So when we're looking at Lewis structures, ultimately all we're saying is that we have 4 sides. Okay? In 3 dimensions, we've got a lot more than 4 sides. I won't count them. 8, 6, 9. Cube is 6? Well, we've got more. Let's stick with that. Where do we put our electrons? The most electronegative being oxygen. So we can now start putting in our electrons. How many electrons do I put around an oxygen?
8.
Put in 8 to satisfy the octet. I don't care how many electrons oxygen came in with in its valence. It wants 8 around it. I'm going to put 8 around it. You'll notice that I'm putting the electrons in pairs. Again, where am I putting them? On the sides of an invisible square going around the oxygen. Okay? That puts in 8 electrons. How many do I need to put in? 16. Where do I put the rest of the electrons? Around the other oxygen. Same process. How many electrons have we put in? 16. Now I go through and look where there are electrons between atoms, and I can then erase those dots. This is why students hate this method, why it's nice for me, because the iPad erases very nicely. And I can convert that into a line connecting those two atoms. Okay? Why do I use the line?
Shows a bond.
Shows a bond. Okay? Another method that you'll typically see older chemists use. Those are pairs of electrons. I can turn it into a line. In case you couldn't tell by the mockingness in my voice. To me, that makes it more confusing. I draw a line because it's a bond. I don't want to draw a line when it's not a bond. It's not a pair of electrons that I'm marking a line for. It's that I have a bond. Okay. Now I go through, sorry? Yes, it does go against my laziness themes. You're right. Mea culpa. I'll accept that. But I get it right, so I'll accept it better that way. So then the next part is trying to move electrons to satisfy octets. So we would go through and evaluate each of our atoms and say, has it reached its octet? We take a look at the oxygens. Have they achieved their octets? Absolutely. Which means they're good. What about the carbon? How many electrons are around the carbon? 4. It needs to have 8. So the first common mistake that students do, right, now it has 8 electrons. Whoopee. What's the problem with that? There's a reason we totaled the valence electrons to begin with. You cannot add more. Okay? So somehow or another, we have to get 4 more electrons towards that carbon. How do we do it? We will move electrons. Hey, that's kind of neat. This is why resonance is a huge argument. What did I say earlier that we were going to do in organic chemistry? Move electrons. What are we doing with resonance? We're going to move electrons to satisfy these octets. Okay? The way that an organic chemist would look at this is say, I'm going to find a pair of electrons and move them towards the carbon. And that towards is a pretty big deal. I can't take these 2 electrons and now put them directly on carbon. Why not? We've only then ruined the oxygen. Okay? So when we're talking about towards, what we're trying to do is only move them as far as we can and maintaining that sharing balance. So what we would go through and do, in the case of this system where we have lone pairs, for the sake of drawing, I'll circle them, and I'll move them towards the carbon. That towards is going to end where? At the position between the carbon and oxygen. So I now have a bond. I don't even want to get into the double yet, but you are technically correct. I now have an extra line. 2 lines means 2 bonds. That's where we get our double bond from. So again, we evaluate, are our oxygens satisfied? Yes. Carbon? No. So what has to happen? We need 2 more electrons still need to be shared in. What 2 electrons do we pick?
From the other oxygen.
Says the ones you move to the other side.
Okay. This is probably how you were trained to do it. And I'm not going to say it's bad because when we get to the next slide, it's technically correct. And we would end up with CO2 for our final structure. Did we have to pick that lone pair? No. Is there another lone pair I could have picked? Are my octets satisfied? Go ahead, count them out. All the octets are perfectly satisfied. Everything is valid within this structure. Why on earth did they not teach you that? Because it has to bring up the topic of resonance. And remember what we said already. Typically in general chemistry, they don't want to open that bag of worms because there are enough other things there. Okay? What we've just generated here is what's technically known as our first resonance structure. Okay? Really, when we're considering resonance, we're typically talking about structures that are all of equal energy. Okay? Well, how do we decide if they're of equal energy? they satisfy all of our Lewis rules. Okay? Are these two structures of equal energy? No. Did we satisfy all of our Lewis rules yet?
Formal charge.
We haven't addressed formal charge. Okay? I again go through a slightly different definition than you'll see in a Gen Chem textbook, and that's because Gen Chem textbooks, primarily the one thing they want you to learn out of Gen Chem, okay, you may or may not realize this, units. That's it. That's all Gen Chem is. I hate Gen Chem. That's all it is. You give me a unit, make me turn it into a different unit. So when they give you a formula, it's how do you convert one unit to another unit. If you take a look at my formula, formal charge equals valence electrons minus bonds minus non-bonding electrons. Why does a Gen Chem instructor flip out at that formula?
It's half the amount.
The units aren't the same in that calculation. Bonds doesn't say anything about electrons. Okay? Why does this definition work? And it avoids that stupid half fraction junk. Half of the number of bonding electrons. Well, how many electrons go into a bond? 2. So if you cut it in half, you get 1 bond. You don't need the fraction. Okay? So we could go through and count our valence minus the number of bonds minus the number of non-bonding electrons. The valence is the one time that we go back to what our atoms came in with originally. So if we start with our topmost structure, our standard structure for CO2, what's the valence electrons on our first carbon? Our leftmost carbon. Actually, didn't matter.
One.
I said carbon? I meant oxygen. Let's try oxygen. What's our valence electrons on our oxygen? I know I switched up. Oxygen is 6, carbon is 4. 6 minus the number of bonds on our leftmost oxygen. 2. Minus the number of non-bonding electrons. How many non-bonding electrons are there? 4. Be careful here. One of the common trends is people will go through and say, well, there's 2. There's 2 pairs of non-bonding electrons. We're asking for the number of non-bonding electrons, period. We're not counting pairs. 6 minus 2 minus 4 gives us 0. What's our formal charge on that oxygen? 0. Where do we write that? We don't write it. One of those lazy things. Why write an extra 0 when we didn't have to write it? 0 is nothing, so why write nothing? If we take a look at the rightmost oxygen, 6 minus 2 minus 4. Same deal. Our carbon, 4 minus 0. Again, 0. What happens if we take a look at our bottom structure? Our leftmost oxygen, 6 minus, let's make sure we get the order right, 1 minus 6 gives us negative 1. So that's not 0, so we have to specify it. Where do we specify it?
Top right corner.
Ooh, that's a fun little tweak. Typically, when we look at general chemistry, where do we put our charge? Upper right corner. Why? In general chemistry, we don't give a crap about structure, which is ridiculous. Organic chemistry is all about building things. When you go to build something, do you care what its shape is?
Yes.
Yeah. So when we go through to put in our formal charge, we need to specify that formal charge on the atom that has that formal charge. So not the upper, okay, I see what you're saying, upper right-hand corner. As long as we're close to it, it doesn't really matter. I would probably write it in the upper left-hand corner, as opposed to right in this case. Why? It gets it far away from that carbon. I know the negative can only be on that oxygen. Okay? So you might see that charge bounce back and forth between left and right. It is typically almost always in the upper portion, of the upper quadrant. What happens when we move to our carbon? 4 minus 0. Okay? So it has no charge. What happens when we move to the last oxygen? 6 minus 3 minus 2 gives us
Plus 1.
positive 1. The charge on that oxygen is positive.
Do we
Okay.
need to circle the charge?
You don't have to circle the charge. I will consistently circle the charge.
Oh,
Okay. The only reason being, particularly when it comes to a minus sign looks an awful lot like a bond, okay, or even a stray mark. So it helps to circle it to identify that that is very clearly a charge. Okay. Both of these structures represent the exact same molecule, but they represent the balance of electrons within that structure in different locations. Perfectly valid to go through and do. The next part of it is, are they of equal energy? Okay, no. Why?
Energies in the
One
bonds.
side has an.
One molecule has 0 charge on every single atom. The other molecule has charge. What did we say was the issue with charge?
It's unstable.
It's unstable, very high in energy. We don't want to be in those states. Okay? Which means when we draw out the structure of CO2, we typically don't look at its resonance structure, okay? At least in 151. Why do we look at the resonance structure in organic?
It's going to be more reactive because it's unstable.
It's not that it's more reactive. It is the exact same thing. Both of these structures represent CO2 equally. Okay? Perfectly valid structures. So we can't say one is better than the other necessarily.
Because C1 gets the lowest energy state, so you pick the one that's more stable.
We typically look at the first resonance structure because if I'm going to try and figure out how CO2 reacts, what do I want to find within CO2? Charge. There's a negative charge on the oxygen, which means how could CO2 potentially react? It wants to react with something positive. How do we purify air of CO2? It's one of the things we can do with it. So I'm pretty sure this showed up on an ACS test, actually. Typically bubbled through water. What happens to it when it's bubbled through water? It reacts with the hydrogen ions in water to make carbonic, or technically carbonate, or hydrogen carbonate, and the CO2 is then trapped in the water, okay, as that new structure. If we only look at CO2 as the double bonds, we don't see those charges. We have no idea about their reactivity. As soon as we look at that first potential resonance structure, we can start to predict something about how it's going to react. Turns out CO2 can act as a base by collecting hydrogens from water. It can also act as something known as an electrophile. Okay? Electro sounds like electrons, phile, love. So CO2 can act as an electrophile. It wants electrons. What part of CO2 is going to act as an electrophile? Who said it? Okay, we've got the oxygen on the right being positive, which becomes tricky. Okay, it is positive. Can it accept more electrons? No, why not? It's already got its octet. What is carbon doing right now to, or sorry, oxygen doing to alleviate that positive charge? It is stealing those electrons from carbon. Carbon then is missing its octet. Carbon can now act as our electrophile. Okay? It takes practice to go through and manipulate the structures and see how the electrons shift through it. Okay? We just jumped from drawing Lewis structures, arguably 151, to the tail end of organic chemistry, okay, by looking at that reactivity. It's a pretty big leap. Okay? I want to show you where you can go from this. Okay? Let's take a look at another structure. One that has potentially, or sorry, not potentially, one that does have legitimate resonance. Is that a yes? Okay, let's try that. Structure that's good for legitimate resonance. CO3 minus 2, also known as the carbonate ion. How many valence electrons does carbon have? How many valence electrons does oxygen? How many oxygens? What else do I need to do? I have to add 2 more electrons to do why? Why did I do that? To account for that charge imbalance that is specified, yes, in the upper right-hand corner. How many electrons? 4. If we go through and set this up again, since I actually already know what the answer is, you'll see me space the oxygens in this fashion. You don't have to space them in that direction. We would then go through and put in our electrons. Oops, should have put them there first. How many electrons have I put in? 24. So I'm now done putting in electrons. I can convert in some bonds. Okay, going through that whole erasing process, which, yes, takes more time. Here's where I argue the biggest difference shows up. With legitimate reference or resonance, okay, if you go through by putting electrons around the central atom first, you most typically only see one resonance form. You end up dropping a double bond, you take one of those lone pairs and you shift them towards an oxygen. If you draw it out in this fashion, we see that that carbon is electron deficient. It's missing electrons. Where do we get electrons from? From the oxygen. If we got those electrons, would oxygen be, or carbon be satisfied? Yes, so I only need one pair of electrons. Which pair do I take? Every single one of those is a valid option on each of those oxygens. Which means if I ask you to draw the Lewis structure for carbonate, how many structures do you need to draw? 3 to represent each and every single one of those possible resonance structures. What electrons were we moving when we look at those resonance structures? We're looking at lone pairs, and those lone pairs are going in to make what? The double bond. It's the second bond. So when we're looking at resonance, the only electrons that we can move are going to be multiple bonds, so double or triple bonds. We can move a pair of electrons there, or lone pairs. We're not allowed to touch the single bonds. Okay? Those single bonds are fixed permanently in that position. Because what happens if I move the single bond?
Oxygen's not associated with it anymore.
I no longer have that connection. At best, okay, I end up moving that oxygen somewhere else, but now I've changed the structure. It's a different compound potentially. Okay? And resonance is a bit weird in the respect that when you look at these, okay, the natural response is, what is the difference between these? Well, you say nothing, because all you did was rotate it. Okay? The way we can get around that, did I rotate it? No. Okay? Technically, I guess I have to go through and specify another oxygen too. Okay? When we're looking at resonance, we pin the structure. We can't flip, rotate, or move it. Okay? It is now pinned in that location. That's how we will evaluate it. Okay? That will change in the future, just so you know. Okay? If we're really careful with this, you take a look at the carbonate ion that we were given as a prompt. It says -2, which means what charge needs to show up on each of our structures? -2. Okay? How are you trained to do that in Gen Chem? Brackets. That says the charge is somewhere in the structure. Sorry, that's too vague. What do you have to do? You have to put a formal charge on the correct atoms. Okay? With a little bit of practice, you should end up finding out that the oxygens with only a single bond are the ones that are negative. And since I drew them all the way out, I've got to specify all the answers all the way through. Okay? Almost. Not quite. I got 30 seconds. Okay? So that's what we're looking at with our Lewis structures. Okay? Resonance is a really, really important aspect. We will be ending on this. Don't stress too much on that. Okay? What we're looking at is the ability to arrange a compound's electrons. And in particular, and we're going to get more specific with this definition as we start to add more layers onto our vocabulary, we're looking at pi electrons and lone pairs. Those are the only electrons that we are allowed to move. Okay? If you want to go ahead and do this one at home, the cyclopropenyl cation, I don't expect you to know what that structure looks like yet. So there it is. Crap. We haven't talked about that notation yet either. Shoot. Here is one Lewis structure for the cyclopropenyl cation. You should be able to draw some resonance structures for that compound. Okay? So give it a shot, see what you can do. That is the end of lecture, so feel free to pack up.